let's talk about chemical equilibrium and review that for just a moment. So chemical equilibrium occurs when a reaction is reversible and it's happening in a closed system. A reaction is reversible when some of the products can actually reform into some of the reactants. And in a closed system, the matter doesn't leave. And so this process can happen over and over until the rate of the forward reaction and the rate of the reverse reaction are equal. And what happens is the amounts that are present stop changing. And we saw this in our lab. Here's the data that we took from a group, and you can see that around time 4, they've reached equilibrium. The amounts of A and the amounts of B are no longer changing. Now, we express equilibrium through something called the equilibrium constant or the equilibrium expression. And it's written as the concentration of the products over the concentration of the reactants. And when we write equilibrium constants, we will not write any solids or liquids because they have no effective changes in concentration. But this value of K can tell me about the favorability of a reaction. So when K is less than 1, what this tells me is that there are more reactants than products. And so this reaction favors the reactants, and it isn't a favorable reaction in the forward direction. And so we can actually say that delta G is going to be greater than 0 for the forward process, or that the reaction is not favored in the forward direction. If the concentration of the products is greater than the reactants, then we'll get a value of K that is greater than 1. And this means the reaction does favor the products, and it is going to go more forward than it does in reverse. And so for this, we say that delta G would be less than 0. The concentration of reactants and products being close to each other tells me that the value of K is pretty close to 1. And it would be kind of hard to guess which way delta G is, other than saying that we know it's above or less than 1. When I look at Ks, I can also use numbers that are much, much larger than 1 or much, much smaller than 1 to make kind of a more general blanket statement. And that is that if a K is much greater than 1, this reaction proceeds to completion. All the reactants are going to turn into products, and the chance of the products turning back into reactants is really low. If the opposite is true, where K is much, much smaller than 1, then virtually none of the reactants are going to turn into products. And so this reaction doesn't happen that much. Now, we're not always at equilibrium. And so for a system that's not at equilibrium, we can define something that we call the reaction quotient Q. And this is basically the exact same thing as K, but we're checking to see if we are at equilibrium by plugging the numbers into this value Q. It's written exactly like K would be. The only difference is the numbers might not be at equilibrium. We actually use Q to determine which way the reaction is moving to try to reach equilibrium. So if I plug in numbers and I compare Q to K, and Q turns out to be less than K, this reaction is not at equilibrium. There needs to be more product to form. And a simple way to remember this is to write Q and K on a number line. And Q is always trying to make it to K. So if I draw an arrow from Q to K, the arrow will tell me the direction the reaction needs to go. So in this case, Q is going towards K, it's moving to the right. That means more product needs to be made. If Q is greater than K, the reaction's still not at equilibrium. This time we're past equilibrium. More reactants need to form. So we'll see that Q is going to go towards K in the opposite direction. When Q and K are the same, that's when we know we're at equilibrium. So that'll take care of our quick review on equilibrium. We'll get into the math a little bit later on.